If you're starting a course in econometrics, regression analysis, or really a number of other related courses, one of the earliest topics you're likely to encounter are the Gauss Markov assumptions. So what are they? Hello, welcome back to the Quant Plus YouTube channel. So as we alluded to in the introduction to the video, we will be discussing the Gauss Markov assumptions. But before that, I wanted to bring you up to speed, at least partially, on ordinary least squares regression, or OLS regression. OLS regression is pretty much a fancy way of saying the line of best fit. It's where we're trying to fit typically speaking, a straight line through our data. And in the example I have here, we're fitting a model of the form y equals beta 0 plus beta 1x plus some error term u to our green points representing our data. When what we can see visually is that this is pretty much a straight line, and we can think about it in terms of algebra as being mx plus b, right, where m is your slope and b is your intercept value. As I've written it out here, we have beta 0, which is our intercept value, plus beta 1x, so beta 1 is our slope, and then u is some error term pretty much accounting for differences between what our model predicts and what we actually observe. So we have this quantity called the residual, which is defined as y minus y hat, or the true observed value minus the value predicted by our model, and we label that the residual. And then our goal is to find the values of beta 0 and beta 1 in this particular case that minimize the squared residuals, or the sum of the squared residuals, meaning for each point there's going to be some kind of vertical distance between our observed value and that value predicted the value that is predicted by our model. So if we square each of those and add them up, then that gets us a measure of how well our model fits the data, and we want to make that error term, right, that vertical distance on average, as small as possible. So next we're going to discuss the assumptions that really underlie that model. And so these assumptions apply for both the simple regression model. It's very similar to the example that we were discussing earlier, where we have a single x, or a single explanatory variable, that is being used to predict, that is being used to predict or calculate our best guess for our output or dependent variable y. And it also applies for when you have multiple x's that you're using to try and predict your y value, called a multiple regression model. Now, the first assumption is linearity. And without getting into the finer mathematical details, you can think about it visually as a straight line of the form mx plus b will fit our data pretty well and explain the majority of what's going on, right? And I think the best way to think about linearity is when we do not have linearity. So if the curve that is closest to the most data points is really like the shape of a parabola, or a semicircle, or some other shape that is not a straight line, we know that we do not have linearity. One of our assumptions is that we do indeed have linearity. The next assumption is that of non-collinearity. It is a slightly fancy term, but pretty much it's saying if we have multiple x's that are explaining or being used to predict our y variable, then, and as I've written out here, x1 should not really affect x2 and vice versa. So I used this particular example in a previous video, but let's say you're trying to predict fuel consumption of a vehicle according to different characteristics of the vehicle, such as maybe brand, age, type of vehicle, engine size, etc. And if you were to include both your engine size and the number of cylinders, then, well, engine size and number of cylinders typically go together, right? A larger engine, let's just say by volume, um, will typically also have a larger number of cylinders, and having a larger number of cylinders and having a larger engine size are both correlated with or associated with um, using more fuel. And so there are a number of potential issues that can occur if this assumption is not met. And there's an extreme case called perfect collinearity, where let's just say x1 is a direct function of x2, right? And for those of you with a bit more experience, think about that as a system of equations where you have, let's just say, two variables that you're trying to solve for in one equation, and then you're going to have an infinite number of solutions. The third assumption I've written as the correlation between the xi terms and our error terms is zero. So visually, we're saying that the error term is pretty much the vertical distance, right? So as an example, the vertical distance here between that last green point and our blue line is our error for that particular data point. And maybe more intuitively, more conceptually, we can think about our error as being comprised of or composed of the other things that maybe should be in our model, or at least have some kind of correlation with our y variable, the one that we're trying to predict, that aren't necessarily included in our model. So to give you an example of that, let's suppose that you're trying to predict someone's weight according to their height. And that while that may give you a pretty decent prediction, there are other things that are typically correlated with changes in weight that we're not including in that particular model, right? So things like gender, age, ethnicity, location in the world, and so many other things that you may consider. All of those things have some kind of correlation with your y variable, but are not being included in the model as it was stated, and therefore all those terms are going in the error. How it's written here, the correlation between xi and the error term should be zero, is pretty much to say all the variables that are included in the model do not have any kind of association or correlation with error terms, meaning things are not included in our model, and so we therefore believe that our coefficients are accurate representations of the effects of different explanatory variables on the dependent variable. So to give you an example of that, let's say we're trying to predict someone's income, and if the only thing that we try to use to predict someone's income is, let's just say, their number of years of work experience, well, we know that it would typically make sense to include someone's level of education as well, right? In terms of, let's just say, the number of years of education. And because we're not including that in our model as it was stated, there's going to be some kind of the education variable is going to be in our error term. But what we also know is that if someone is in school, they're not typically gaining years of work experience. So as years of work experience increases, years of education decreases, or maybe more accurately stated, the more time someone spends in school, right, the more education they have, the less work experience they have. But because we're not including that in our model, the one coefficient that we have that is measuring the effect of, let's just say, years of experience is no longer accurate, right? Because it is accounting for both the effects of work experience, and it's also accounting for the effect of education that we're not including in that model. The fourth assumption is that of homoscedasticity. Essentially what homoscedasticity means is that if we look across our different data points, we have a fairly consistent distance between our data points and our model. So that's the sketch on the left, where we can see that the distance between our green points and our blue line representing our model is fairly consistent across all our observations. In contrast to the sketch on the right, that is heteroscedastic, meaning if you can see how here, around here, we have a smaller distance on average from the blue line representing our model as opposed to here. So when our x values change, so will our variance values. And that's heteroscedastic. The last two assumptions, I didn't number them because depending on the source that you use, this assumption may be stated, these assumptions may be stated and they may not be. The first one is that the variance of x is greater than 0, meaning that you have multiple data points and they're not all in the same exact x value, right? So if you think about this in terms of a geometry or algebra type thing, you need at least 2 points to define a line, right? So if you have 2 points with different x values, then voila, you can stick a line through those 2 points. Whereas if you have only 1 point, then you have an infinite number of lines, right? You don't have enough information to pinpoint it to one particular line. Or you might have a scenario where you have multiple data points, but they're all in the same x, and then you get a vertical line. This has an infinite slope, and that really doesn't really doesn't lend itself well to analysis. It doesn't lend itself well to explaining the effect of different x's on your y variable, or vice versa, using multiple x values to predict your y value. And the last assumption that some sources list, others do not, is that your data is coming from a sample, right? It's coming from a random sample that's representative of your population. And ultimately, if you had every data point in your population, then there's really no point in trying to fit a regression model to it, because a regression model can typically either be used for predictive purposes, right, predicting the value of your output variable, or for causal inference, which I've discussed briefly in another video, pretty much trying to accurately measure the impact of different explanatory variables on your dependent variable. And when these assumptions are met, then your ordinary least squares regression model is quote unquote blue, or your best linear unbiased estimator. Long story short, it is a good fit for your data. If you found this content informative, please support the channel. You can do that by liking this video, sharing it with your friends and family, subscribing to the channel, and really get it out there. I appreciate your support thus far, and if you're interested in one-on-one tutoring sessions, please follow the link in the description below. Have a great day.